Okay, the 2023 questions are out. I'm going to work the set, I believe this is set 1, I think. I'll have to look at that before I post it, but this is the one that my students identified with that I have seen this. They said, yeah, that's what we saw, so this is the one I'm going to do first, and then later I'll go and catch the other one. And again, this is my first run at it, so I can make mistakes, so don't be too harsh, criticizing, well, you should have done this, because this is my first time too. So scientists have created a new type of lightweight foam and are performing experiments to investigate the properties of the foam. The mass of cart A is 1,000 kilograms. The mass of cart B is 2,000. So I'm going to write that down. That's 1,000. This is 2,000. All right, and it says a piece of foam with negligible mass is attached to the front of cart A is shown. Cart A moves with a constant speed. We don't know what it is, but it's V naught of some sort toward cart B, which is initially at rest. So its V naught is 0. At time 0, the foam makes contact with cart B. It remains in contact for 0.5 seconds, which is our delta T, after which the carts separate and both carts move with constant velocities. So I know my story. So on this first one, it says here's a graph, and it shows, let me pull that down. It shows the velocity as a function of time for the time interval when the foam and the cart are in contact. What feature of the graph could be used to estimate the displacement? Well, this goes back to our calculus knowledge. This is delta x, and since velocity is the derivative of position with respect to time, delta x would be the integral of velocity with respect to time. So we want the area under the curve, and that's what I would have written as area under curve. Using the information in the graph, determine the speed of cart B at a half a second. Now this kind of confused at least a student or two that I talked to. They thought they had to actually, do some function with the graph, but we just need to get some information from the graph. So because this is a collision, I'm going to do P naught equals P final. So that means mass A, VA naught, plus mass B, VB naught, is equal to mass A, VA final, plus mass B, VB final. So I'm doing my conservation of momentum. A is 1,000, moving at V naught, which, by my graph, I can look at my graph, what's V naught? I'm going 5. So I'm going to put that in there. Plus the mass of B, don't really need to put that because what's B doing in the beginning? Nothing. Okay, is equal to the mass of A, which is 1,000. Moving at VA final, again, I can get that from my graph. There's my VA final right there, 1. Plus the mass of B, which is 2,000, times VB final. So over here I get 5,000 is equal to 1,000 plus 2,000 VB final. I can subtract that 1,000. I'm going to move that up here. I get 4,000 is equal to 2,000 VB final, and I'm going to divide by 2,000, and I get 2. And that is my final velocity of that cart. It says on the following grid, draw a smooth curve of the velocity as a function of time. Okay, so this is the velocity of B as a function of time. Now, remember that A is smaller than B, and they experience the same force. So they have the same force, but since A is smaller, its A will be bigger. Now, why do I care about that? Well, the slope of this line is acceleration. So I need a flatter slope. I'm looking for a flatter slope. And so what do I know B does? It starts out at 0, and then where does it end up at? Well, I just found that it ended up at 2. And so it's going to have a graph that looks a lot like A's, just a little backwards. Okay? Now, the thing you want to make sure here is my change in momentum, I go from 5 to 1. So that's 4 times 1,000 is 4,000. That's the change in momentum of A. It changes by 4,000. This one experiences the same change in momentum, just in the different direction. It goes from 0 to 2. 2 times 2,000 is 4,000. And okay, that makes sense. I've got the same change in momentum. Okay. Now we do calculus. For time 0 to 0.5, the velocity of cart A can be described by this function. So I'm going to write that function. Velocity is 64t cubed minus 48t squared plus 5. And they want to know the maximum force. Well, I know that force is mass times acceleration. Okay, so I'm going to need acceleration. So acceleration is going to be dv dt. So I'm going to derive this. So I get, let's see, 180 and 12. That's 192 t squared minus 96t. And then that one goes away. But they want max force. So I need max A. How do you get the max of a function? You take the derivative and you set it equal to 0, right? So A prime is going to be the derivative of this, which will be what? Let's see, it'll be 384 minus, or 384t, excuse me, minus 96. And I'm going to set that equal to 0. So 384t is equal to 96. So t is equal to, I'll divide this by 384. And I get 0.25. That's a fourth of it. Okay, so that's my time. So my mass, and this is cart A, so I'm going to use that mass of A, 1,000 kilograms, times this maximum acceleration, which is 192 times 0.25 squared minus 96 times 0.25. Now let's see, I'm going to get my calculator out here because I don't want to do that in my head. All right, and I get a negative 12,000 newtons. Okay, this makes sense though. A was moving forward, it gets a negative force on it. And if I went over here and I actually looked at this slope, I wouldn't be too far off with that value because it goes from about 4 to 2, so it goes down 2 in about 0.1, 0.2, 0.2 and a half, so 0.25. So we can take that, find the acceleration, then multiply by the mass, but they wanted us to use this function. So this is what we did. All right, now it says, on the following grid, draw a smooth curve. Okay, if I were you and I was on the test, I would do this. Since force is equal to mass times acceleration, you've got 1,000 times 192 t squared minus 96t. I would just plug that in my calculator, and it says to indicate the value of the maximum force on the scales. This graph's kind of weird to scale because 2, 4, 6, 8, 10. I can't do it by twos. So I decided I'd do 3,000, 6,000, 9,000, 12,000. Or you could just indicate, you know, force max. You could just say, okay, this is going to be F max right there. But that's my max, and that happens at 0.25. So I'm going to peak out right there. But what is this? It's a squared, so we know it's going to be a parabola, and so we're going to start off with a big force that's going to lessen over time, or not lessen over time, excuse me, increase over time. It's going to change less over time, and then we're going to go back down the other way. So this is what our shape should look like, and if you put that in your calculator will spit that right back out at you. Just use those graphing calculators to look at that. Okay, now, last part. We're going to take the foam out of the cart, and we're going to remove that, and we're going to repeat the experiment. So they're going to collide now. Everybody has the same initial and final velocities. The time intervals during which they're in contact, though, is different than when they had the foam. In the collision without the foam, they're in contact for a shorter duration. And it says for the original collision when the foam is present, the magnitude of the average net force is F1. When you take away the foam, it's going to be F2. What is the relationship between F1 and F2? This is a lot of words that can get really confusing. But the thing that I noticed that sticks out to me is there's a shorter duration of time. And they're talking about average net force. So I go back to our equation. We call it FATMAV around our parts, but this is the impulse momentum principle, such that if we have the impulse, it's going to equal a change in momentum. So F is mass times velocity over change in time, which, what is that? Mass times acceleration, like that's the same thing. But What are we adjusting? This is the same, okay, for each of them. This is the same for each of them. So this top is going to be same for whichever, we're talking about B here, but it's going to be the same for either force. The top is going to stay the same. But this changes. So when it's F2, delta T is smaller. And when you divide by a smaller number, then F2 is going to be bigger than F1. So F2, alligator eats F2, go with the bigger one. And we justify our answer by this over here and saying since the delta T is smaller, the force must be larger to maintain the same change in momentum. Because if we're going to have the same change in momentum, we got to have the same stuff up there. The mass and the velocity is going to be the same. And so when we change the time, that's what we mess with. All right, and that's question 1. Okay. Let's move on to question 2. So question 2 has some springs. Springs are scary always, right, as physics students. We've got some springs, and they've got a box hanging from these springs. Now, before I even do anything, I'm going to just free body diagram so I kind of have an idea. I've got mg down, and I've got kx up. Over here, I've got mg down, but up, I've got 2 kx's, right? There's 2 of them pulling up on this instead of 1. So